A high-speed train weighing hundreds of tons floats slightly above its track, moving at over 300 miles per hour without ever touching the ground. The exact same mechanism aligns the tiny needle inside a pocket compass. We are completely dependent on this force for transportation, energy generation, and basic navigation. Yet the physical rules governing how it operates are entirely invisible to the naked eye. At the most basic level, magnetism is governed by interaction. Bring two north poles or two south poles together and they push each other away. Bring a north and a south pole together and they attract, pulling physical objects like these metal clips right to their surface. This raises a question. If the north and south ends do different things, what happens if you snap a magnet straight down the middle to isolate a single pole? You don't get an isolated north and an isolated south. Instead, you instantly get two complete smaller magnets. Every single physical magnet in existence always has both a north and a south pole. Because these poles cannot be divorced from one another, magnetic energy doesn't just shoot out in a straight line. It has to flow from one end to the other, creating a continuous loop. To calculate and predict these loops, physicists illustrate them using a system called magnetic field lines. Magnetic field lines always flow outward from the North Pole, curve through empty space, and re-enter at the South Pole. Where these lines are tightly packed at the poles, the magnetic pole is strongest. As they spread apart, the force gets weaker. To quantify exactly how strong that field is in a specific area, scientists measure it using a unit called the Tesla, named after Nikola Tesla. This mapping system applies to the smallest bar magnet and scales up perfectly to planets. Earth generates a massive magnetic field extending far into space. But there is a catch when we navigate by it. Because opposite poles attract, the north end of your compass needle is actively being pulled toward the Arctic. That means Earth's geographic north is actually a magnetic south pole. Whether you were steering a cargo ship across the Atlantic or sticking a grocery list to your refrigerator, the exact same invisible architecture is holding things together. To understand where this architecture comes from in the first place, we have to scale all the way down past the visible surface, right into the atomic structure of the metal itself. Inside materials like iron, atoms group together into microscopic clusters called ferromagnetic domains. You can think of each domain as its own tiny compass needle, pointing in a specific direction. In a regular piece of iron, these domains point randomly in every direction, canceling out each other's push and pull. But when you expose that iron to a strong external magnetic field, those microscopic domains snap into place and perfectly align. Their individual forces compound to create one strong, permanent magnet. But this alignment is fragile. If you apply extreme heat, reaching the Curie temperature, thermal energy causes the atoms to vibrate violently. The domains shake themselves out of alignment. Macroscopic power is entirely dependent on this microscopic discipline. Break the internal alignment and the invisible force simply vanishes. By figuring out how to force these microscopic domains into alignment, engineers have learned how to manipulate heavy physical objects using only fields. Looking at this maglev train, the track and the underside of the train are equipped with magnets, facing the exact same pole toward each other. The resulting repulsive force is strong enough to levitate hundreds of tons of metal, eliminating track friction entirely. In medicine, massive coils create magnetic fields of several Tesla. When a patient goes inside an MRI machine, that intense field physically aligns the protons inside the water molecules of their own body, generating highly detailed internal images without a single surgical incision. And when we cross these fields with moving electrical charges, we generate physical rotation, the basic mechanism driving the electric motors in everything from cooling fans to modern cars. Let's do a quick check to lock in the 3 physical laws that make all of this possible. First, the rule of pairs. What happens if you snap a magnet straight in half? Second, the mapping rule. When looking at a diagram of field lines, what does tightly packed line density indicate? And third, the planetary rule. In terms of physics, why does the north end of your compass point toward the Arctic? You can't hold the field itself in your hands, but the physical results are everywhere. By figuring out how paired poles loop together and how aligned atoms compound their strength, we built the tools to reach across empty space and move the world.